Bismillahirrahmanirrahim. Assalamu alaikum warahmatullah. I'm Mohammed Ismail Hussain. This video is sponsored by Seismic Consulting Engineers. Today's topic is special shear wall design using a test program. The video courses related to this will be available for free to everybody and can watch and download the videos from the link given below or in the web page. So are the audiences for whom this video is actually dedicated to. So as an consulting engineer actually wants to create some resources or knowledge bases so that the young colleagues can understand or learn the design procedures adopted by the senior engineers. Also, these videos will be made available to everybody so that they have any lack in understanding or they want to better understand the design concepts, they can go through these videos and learn in detail. So in this video lecture series, we will not go through the code requirements in depth, actually. Rather, we will go through the structural model and try to design a structural shear wall, all of its components, starting from the flexural reinforcements to the boundary element, everything. At the beginning, the part 1 is dedicated to the introduction to code requirements and practice. So at the beginning of the code discussion on code requirements and etc., I would like to focus on a few documents which I think that the engineers, young engineers, should study first before going into the design of these structural walls. So prior to designing anything, any component such as be it a retaining wall, be it a column or a beam or a slab or a structural shear wall, the designer should have some preliminary understanding of the design component. So we all study these items in our undergrad, but still in design practice, those understanding actually doesn't last too long. So we have to refresh our knowledge again. So the documents I would suggest to study, one of them is the ETABS document for shear work. You can find it from here. You can go to the help and then documentation and shear wall design. Then you can choose a design code. Say I'm choosing 31808, and this document has opened. From it, you can there's 32 pages, so I think it won't be very tedious document to read, but you can at least read the important items from here. So this document discusses how to design a wall considering CNT method, compression, tension, flange method, or edge zone method, and then uniform reinforcing. And then the the third one is, let me check it out. The third one is the general fire section method. So there are 3 methods. This document discusses all of those methods. Okay. So to gauge the theoretical knowledge, I would suggest to study the book of White and McGregor, the Reinforced Concrete Mechanics and Design, 6th edition. So in the 18th chapter, you will find walls and shear walls. The basic design principles are discussed in this chapter. So you will know how this works. Okay. So you see the bending moment here, how the bending moment works in a shear wall. At the top, is something 0, then it gets something positive or negative value, then the reverse sign develops. Also, some guideline is provided, distribution of walls in a building floor plan, how to locate the shear, so then there are minimum eccentricity, torsional irregularity, etc. Then the book goes on to designing the structural shear wall, considering the beam concept, which is known to all of us. Then in the 19th chapter, there is another part designed for earthquake resistance. There you will find the requirements for structural shear walls. Starting from here, joints not there, structural diaphragms. structural walls, 1911 structural walls. So you'll have here the idea of how to design a boundary element, how much hoops reinforcement you have to provide in the boundary element, etc. Or how long do you need to continue with the boundary element, or the hoops reinforcement? What is the practical limit of continuing that? This information you can find there. Then we have the code requirements such as the BNBC 2020 in Bangladesh, and which is actually a copy of ACI 318. And most important of all, I would make it a mandatory document to study. This is this one. NEHRP Seismic Design Technical Brief number 6, Seismic Design of Custom Place Concrete Special Structural Walls and Cupping Grids. This document is very, very important. If you study this document, then these other documents are necessary for you to study. However, you may need to go through the code requirements, because code requirements vary from year to year. So you must consult your code. And how ETAPS works, if you want to get some idea, then you can go through the ETAPS documents. So at first, I will lead you through these documents for a few minutes, then we'll go into the main design part. Okay. So the document discusses how the walls should be laid out in the plan, so that there is mineral centricity or torsional integrity, etc. when you should use the structural walls. So it is basically when you can use large cross sections such as columns, or when you need to control your building drift, etc. Then diaphragm connectivity is discussed here. By cords and collectors, you have to connect your diaphragm to the structural shears, wall foundations. So it is very important. Sometimes we miss this part. So shear wall is always a fixed support. Okay. So here it is compression, here it is tension. So there is always a bending moment at the base. So you must design your foundation for the associated bending moment. Okay. If you do not design for the bending moment, then your shear wall concept used here will not work actually, because your foundation will rock before the bending moment can develop at all. So it will not be any logical thing at all. Wall configurations. So these things are nothing very special. You can choose any of the wall configurations provided here. It may be a rectangular shape, maybe a barbell, they call it. So two rectangular column shape at the end, and one lower thickness member at the middle. So it's totally fully a single member. A T-shaped wall or L-shaped, C-shaped, etc. In lift cores, we basically use the C-shaped cores. If there are two lift cores, one is here and the other one is here, then you may end up using a C-shaped, I-shaped lift core walls. So the most important thing, one of the most important thing is this one. What should be the river layout, river detailing in a special structural wall? So this one is actually for a special structural wall. You have the boundary elements at the ends. Okay. So this one is your boundary element. This is another boundary element. Okay. So in this boundary element, you use the transverse reinforcement or hook reinforcement to confine all these vertical reinforcement. Otherwise, these vertical reinforcements may buckle under extreme compression. Okay. So this boundary hooks reinforcement provision is very important. Then you have this long reinforcement. This is actually the shear reinforcement. Horizontal wave reinforcement is actually the shear reinforcement. Shear reinforcement is taken into the boundary element and then given a standard hook if necessary. If this length is long enough, then standard hook is not necessary. There are code provisions regarding that. You can study them always, all the time. Vertical wave reinforcement, and here you can see that there are some major reinforcement here. These reinforcements, the reinforcement detailing can be of many types. You can provide same reinforcement all over the wall, say 20 mm at the rate of 5 inches center to center. And then you can have a boundary element at the edge. Otherwise, you can have a higher concentration of reinforcement at the boundary element or at your edge zone, and then a lower distribution of reinforcement, lower area of reinforcement. Okay. Say, for example, you have here 25 mm at the rate of, say, 4 inches. Okay. So there are so many reinforcement. You have added here some reinforcement at the middle as well, whereas you don't have middle reinforcement here. So you can add middle reinforcement here, or in whatever fashion you may find feasible or logical. You can add your reinforcement. to make the wall adequate. However, in the rest of the wall, the middle part, you may provide giving the distribution reinforcement the minimum one. It may be 12 mm at the rate of 8 inches or 12 inches, etc. Or maybe you can design a general pier section in your ETAPS model and then model this and the middle part as well, and ask your ETAPS model to validate its capacity, whether it is okay or not. So there are a lot of ways to detail your wall. So wall reinforcement, I have given you a little idea about it. Wall proportioning. So wall proportioning, there are actually no code requirements about the minimum thickness required for a wall. So minimum practical lower limit is 8 inches. Okay, so you should not go below 8 inches. However, in any structure, in any residential, commercial, or industrial building, we do not provide any wall lower than 12 inches in practice. So 8 inches is the practically lowest possible. Nothing lower than that can be provided. So the NEHRP or FEMA suggests using a 12-inch thick shear wall for where boundary element is involved. And when coupling beams are involved, then they suggest a 16 inches thick wall. So when you have a structural wall, you have earthquake force or wind force. We are basically talking about earthquake force. So when earthquake is going towards this direction, then you have compression here, then tension here. So cracking in the tension zone, and your concrete cracks here, and your concrete crushes here. If the compression force is very high, your concrete will crush here, and your concrete will crack here. So your maximum bending moment develops at the bottom. However, the bending diagram is not always like this. The bending diagram is kind of like this. It goes on at first like this. What am I drawing? Click online. Goes on like this, then becomes like this. So this line, thick line, is a required bending moment, is the applied bending moment in your model, and this dashed line is the provided bending capacity. So what are the types of a shear wall you can have? There are two types. One is a slender, other one is a squat walls. Squat wall is very uncommon, and in our practice, it's not. It does not occur in our structural design. Slender wall is the common one. So you have to take care of these fundamental design requirements, such as you have to achieve ductile flexural yielding. So you should keep in mind that you will let your wall form a plastic hinge here by yielding your flexural reinforcement. But at the time of the yielding of the flexural reinforcement, your wall should not fail in shear. So it means that you are allowing your wall to achieve that ductile flexural yielding, whereas you avoid shear failure. Okay. So for example, when may shear failure can occur? When can shear failure occur? Say for example, this wall is very large and it attracts a bending moment of say 10,000 kip feet, and the corresponding shear is, for example, 1,200 kips. Say for an example, it's 1,200 kips. So your bending moment, applied bending moment, is 6,000. Maybe that's what I said, 6,000. But you have provided a reinforcement of say 5,000, and the shear force, applied shear force, is 1,200 kips. But let's say otherwise, your shear wall has a bending moment, applied bending moment of 6,000 kip feet, and you have provided 6,000 kip feet bending capacity to it by providing adequate reinforcement. However, you did not provide enough shear resistance to the wall. Then shear failure will be a very imminent case. And also, there are other ways of having shear failure, which we will discuss when we go through the model. Squat wall is not common, so we will not discuss about it. Diaphragms and foundations, these we are not covering here. Building analysis, guidance, analysis procedures, statements, recommendations. Regarding the standards recommendations, when your wall is cracked, you consider 35% of the cross section properties, and when your wall is uncracked, you consider 70%. So this is the common practice we use. Otherwise, there is another suggestion that you can use 50%. Foundation modeling, and this is very important topic here. Foundation modeling, whatever support condition you consider below a foundation, it doesn't actually matter. If you consider a fixed foundation, then your wall is going to resist some out of plane bending moment as well. If you provide pin foundation, your wall will not resist the out of plane bending moment. By out of plane bending moment, I mean each segment. Say if I consider this segment, the selected segment, this wall will not resist an out of plane bending moment. However, it doesn't matter whether you provide here pin or fixed, your wall will resist bending moment in the in plane. Okay, in plane bending moment will be there always. Okay, so for example, if I show you the bending diagram here, see there are 6,700 bending moment at bottom. So it's at 0 and it increases like this and then becomes 6,700 at the bottom. So it means that the consideration of pin here doesn't make bending moment 0 here, because 2 pins make a wall rigid along its plane. So it has infinite bending stiffness based on the support condition. However, the bending moment that will be attracted will depend on the shear wall's cross section or the moment of inertia. So some engineers, young engineers, think that since they have considered pin here, they do not need to design their foundation for the bending moment. This is totally wrong. You have to design your foundation for bending moment. If you do not design your foundation for bending moment, then actually the use of this shear wall in your building is totally useless, because you are not transferring the force to the foundation. So what is the use of that wall? Let us go back to the document. The document says that base restraint can have a significant effect on the behavior of structural wall buildings. AC7 states, for purposes of determining seismic forces, it is permitted to consider the structure to be fixed at the base. Alternatively, where foundation flexibility is considered, it shall be in accordance with section that. Unlike a moment frame lateral system, this is applicable for other types of building where we are not using shear walls. Say, for example, if it is a moment frame building, which may be detailed to be fixed or pinned at its base. So if your building is a frame building, then you can consider pin or fixed below your column, and it is permitted to use either of those considerations. But a structural wall will always be fixed. Okay, so that's a basic thing you must know. It doesn't matter what you apply here, your wall is fixed already. Okay. Then load resistance and load and resistance factors. Load combinations are available in our BNBC course, so these are the same. We don't need to take these. For the phi values of flexural calculation, the phi will be 0.9 when the strain is greater than 0.005 and phi will be 0.65 when the strain will be 0.002. So this is the data you input here. It is automatically given 0.65 and 0.9. Okay. So 0.75 is actually not applicable in this in our case, because we do not detail its spiral reinforced boundary element. Then for wall shear, this is important. For wall shear, including shear friction, so there are two types of shear. One is the shear force. Okay, you design your cross section for the applied shear force. This is the wall shear. And shear friction is when you provide a construction joint, you construct a floor, and then after 1 month you construct another floor, or you construct another wall. So wall on wall there is a joint. So that joint is cold. There is no monolithic connection between the concrete. So that is called that you need to design a shear friction design at that joint. So ACI 318 and BNBC allows phi equals 0.75. Except phi equals 0.6 if the nominal strength Bn is less than the shear corresponding to development of the wall nominal flexural strength. Amen. This is very important topic here. We will discuss this in detail when we design our structural shear wall. But let me show you that item from the design preference. Here you see that High shear seismic. This one, it's 0.6. So this one is actually not applicable to your shear wall design. When your shear wall is actually a special shear wall, this 0.75 will not be used. So high shear seismic, this will be used. So it is 0.6 model has this data automatically in it. However, in some condition, you can change it to 0.75 if your walls shear reinforcement satisfies some requirements, which we will discuss in detail in the later videos. So there are some other load factors like importance factors you need to consider. Though BNBC 2020 does not include this redundancy factor, however, ACI and AC considers this. So redundancy factor should be considered. It is basically 1.3. Okay, it is written somewhere here 1.3. So you apply it when, say, for example, your building has a lot of shear walls. Your building is basically resisting the lateral loads by its shear walls only. The columns are used as only not part of lateral force resisting system. They are only, say, gravity frame. In that case, what you will do is say this one, you do not have any column in it. You can say you have some columns, but those columns are gravity column. So what you need to do is you need to remove a shear wall in your model and check torsional irregularity. If, say, for example, at this moment there is no extreme torsional irregularity, but if removing one of the shear walls at any location, so for example, for a trial basis, you have chosen to remove this shear wall. If after removing this shear wall, you end up getting a torsional irregularity exceeding 1.4, the maximum drift divided by average drift is greater than 1.4, then it is called the extreme torsional irregularity. If you end up getting extreme torsional irregularity after removing a structural wall, then it is said that your structure is not redundant enough. So since it is not redundant enough, you need to use a redundancy factor of 1.3. So how can you use it? You can use it easily by going to your load patterns and then say this is your earthquake case, and then in the occupancy importance factor 1, you can use the 1.3. The what is that? The redundancy factor. Yeah, you can use that. Say you have already your importance factor 1.25, and again you need this redundancy factor, then you multiply these two, 1.2 into 1.25 into 1.3. Okay. This is automatically covered in model. So amplification factors, we do this always. So shear will be distributed based on the individual wall segment stiffness or amount of inertia, etc. So the number 4 is designing for multiple load combinations invariably will result in wall flexural overall strength. It means that if you design a wall for one load combination, say under that load combination, you have 1000 kPa bending moment. Okay, so you have provided 1000 kPa capacity to your wall. So there is no overall strength. But if you have 5 load combinations or 6 load combinations, one has 1000, another 1200, 1500, 1800 bending moment, then you are having some overstrength there because you don't know what bending moment your building, your structural wall will face. However, under earthquake, your wall will face that earthquake inevitably. There is no avoiding that. So in that case, for slender walls where a flexural yielding mode is desired, wall shear should be amplified commensurately. So they are saying that your wall shear strength should be increased to account for the flexural over strength. We will discuss this item in detail. For example, when we will discuss these two items are similar. You can ignore this if you fulfill this one. If you provide shear capacity to your wall corresponding to the expected flexural capacity of your wall, then it will be automatically satisfied. So next thing you should know is design shear stress is A to the power F times C BD. Okay. So that is the maximum shear capacity you can have from your wall. If shear force is higher than this, then you need to provide a higher section, higher cross section. Okay. However, although for any individual segment, this can be as high as 10 square root of FMC. It is permitted to be extended or exceeded 8 root of FMC and extended to 10 root of FMC. When you have some compound shear walls or many shear walls in your building, then individual segment can be designed for 10 root of FMC. So this we will also cover this when we go through our model. So if you have a bendy moment like this is your compression part, compression zone, this is your tension zone. So the detailed calculation, if you want to know, you can go through the White and McGregor's book, chapter 18. They have a structural wall chapter in that. So this is a special boundary element. In the special boundary element, you have hoop requirements. That hoops shall be, as per this guideline, b by 3 vertical spacing of the hoops. Okay, 6 dB longitudinal, etc. These requirements have to be fulfilled. Also, this length has to be determined by this formula, maximum of c by 2 or c minus 0.1 L dot. And your shear reinforcement shall be embedded into the boundary element. But when you do not require a special boundary element, you can provide ordinary boundary element. I mean that though your building is though your shear wall is a special structural wall, in part of your structural wall, you can provide ordinary boundary element. Okay, where you can save some money by providing lower volume of hoops reinforcement or ties. Here you see that hoop sets demand has decreased. These requirements are no longer applicable to the ordinary boundary element. However, the boundary zone requirement will be as before. So let us look at this figure. We can easily understand the concept. The code BNBC and ACI, they both say the same thing, that if it can be the boundary element or the hoops reinforcement, actually the hoops reinforcement, necessity of the hoops reinforcement in the boundary element, whether you are going to provide a special boundary element or a ordinary boundary element or a boundary element, depends on the stress in the wall. Okay, if the stress in your wall is greater than 20% of FMC, then you need to provide a special boundary element. Okay, and if it is less than 15% of your FMC, then in between these 2 points, 0.2 FMC and 0.1 FMC, you need to provide the ordinary boundary element. And beyond that 15% of FMC, you do not need any, boundary element requirements. By that, I mean that you do not need any hoops in your edges. Okay. So if your building is a 7-story building or 10-story building, it may require that up to 4 or 5 stories, you may be needed to provide a special boundary element. And from 5 to 7 stories, you may need to provide ordinary boundary element. And beyond that, you do not need to provide any, hoops reinforcement in the wall at all. However, we do not practice this. We provide a special boundary element throughout the height of the wall. And another thing which is of importance is you actually do not need to provide any transverse reinforcement in this portion, in the middle portion. Between these two boundary elements, you do not need to provide any ties. Look at this. There are no ties in here. Or you can look at the first figure, which I have shown you. The first figure is this one. You do not need to provide any ties here. However, for increased redundancy, increased safety and integrity of the wall, you can provide some ties here, one after another, or after each 2 reinforcement rebar, you can provide one tie. And that tie spacing needs not meet this tie spacing requirement. This tie spacing can be different than this tie spacing or hook spacing. So we have almost covered everything. The only thing left is the hoops reinforcement requirement in the boundary element. This can be found in the code, of course. Otherwise, you can consult this book. The BNBC code and the ACI code says the same things regarding the boundary elements transverse reinforcement requirement. The boundary element transition reinforcement shall satisfy the requirements of section 8354. This is 8354, which is actually applicable for special monitoring columns. As shown in figure 688, except equation 687 need not be satisfied. It means that 8354 is applicable. However, this formula is not applicable. And the transverse reinforcement spacing limit of 8354 B1 shall be 1/3 of the least dimension of the boundary element. So this is the B1. This is the B1. Of the B1, it was written here 1/4. However, you can increase it to 1/3. So if your wall dimension is 12 inches, then 1/4 is 3 inches, 12 divided by 4. But the code allows you to divide it by 3. So 12 divided by 3 is 4. So you can provide 4 inches spacing. So there's the boundary elements requirement. I hope I could clarify the code requirements in designing shear walls. In the next videos, we will go through the structural design, flexural design, shear design, boundary element design of the walls from the ETF's model. Thanks for being with us.